several USB sticks. This could very well be on your laptop. So I'm feeding it the next key stream. And I'm already preparing something else here, because we will have to test whether it's the right key still that it finds. Oh yeah, so it did find something already. It sometimes keeps spitting them out as it goes along. So what this did now is take every subsection of 64 bits in this long string and try to crack it. Now in this case, it was successful at position 8. So 8 bits over from the beginning, it did find a 64-bit segment that matched a key it had stored in its data set. Now, can I actually cancel this? No. Well, it wants to run till the end. OK, here we go. So to verify, can you all see this? This is a little bit in the bottom, huh? Yeah. To verify that it is the right key, there's another tool, and this is really the last one. We didn't make this too usable to keep it away from the script kiddies, at least for a little bit. So you still have to move a lot of data around manually. None of this couldn't be automated, though. So to verify it, we need to tell it what packet we were actually attacking. That's this number. Oops, what am I doing here? And since that already matched, we need to give it a second packet that we know was encrypted under the same key stream. And again, this is all just to verify that it's the right key. And that was the result of this XOR that we did earlier, where it didn't find the key. That's now this XOR. So it did find a total of 5 keys that could have gone into the whole process, this 100 times clocking and so forth. And only one of them, of course, matched the packet we were feeding it. Now this, of course, turns out to be the same key we were using earlier to decode the control data, right? So we did just crack an AFF1 key here. Now we did see in our decode, you remember from the beginning, that the call was switching to time slot 5 on a traffic channel. So let's do, using this key, decode time slot 5 as a traffic channel. And this should have given us this file. Just generated this file. I can delete the file again, just to show you that it actually did just create this. So there it is. That's now basically the raw voice file as it's being transferred over GSM. Another open source tool. So yeah, there was one more. Not by us though. This is just freely available on the internet. This translates it into something playable. They can then yeah, I don't know if you guys hear this, but it does speak to me. Let me see. Oops. Well, I don't know if you heard this. Let me turn this up. Oh no, it tries to do some visualization. Yeah. well, now it was echo. But in any event, we just replayed a GSM call we captured from the air. And I think this is now finally all it takes to convince people that it is easy to do so. If you're willing to move a lot of data from command line window to another. Here's all the tools we just used. GNU Radio, as I said, in combination with the USRP radio, you still need some way to interface with the airwaves. Will capture the data for you. Then a new version of AirProbe that has just been committed to the Git or SVN as of today decodes first the beacon channel, then that control channel. It will tell you these packets are encrypted, I can't decode them. You feed them to Kraken, it cracks the key for you. You test with the second piece of that key stream whether you actually found the right key, and you use AirProbe to convert all of this back into a voice file. Besides the interface into the radio spectrum, all that was used here was a normal computer. In fact, we did run it in CPU mode, so not even a fast graphics card, and 2 terabytes of tables that can be downloaded from BitTorrent. This attack can be done from surprisingly far away. For simplicity, we did just replay one side of the conversation. And in fact, I only recorded one side of the conversation. All the data that's coming down from the cell tower, that's being sent in the general direction of the phone, but from very high up. So if you too are very high up somewhere, you can hear this miles and miles away. If you're well positioned in the city, in a few central places high up, you can be intercepting one side of every GSM phone call there is in that city. Intercepting the other side of the conversation is a little bit more tricky. The phones send usually much weaker. They're also in a much worse position for you to see them. And they're generally only sending as strong as absolutely needed to be heard by the cell tower to preserve energy. So to move this to a dual channel interceptor, up and downstream, you have to move fairly close to your victim or the subject of your research, which hopefully is only you, so you're not breaking any laws. But yeah, the second side can be heard from very far away. Now there's other attacks called IMSI catchers. You might have heard of those. They need to be very well within the range of the phone. So to launch a successful IMSI catcher attack, you have to be close to your victim to attack that victim at all. In addition, the attack is detectable. So a phone could notify the user, hey, you're not using encryption at the moment. Please do not make phone calls now. Until that happens, though, people may be victims of IMSI catchers too. An attack that also needs a USRP. So it's not any cheaper in terms of equipment, really. All you're saving is 2 terabytes in hard disk. But an attack that's perhaps more trivial to set up, especially after Chris Paget's demo at DEF CON one of these days. So yeah, IMSI catcher, much lower range and detectable. This stuff works from a long range away. One more slide with technical details before we can actually talk about what needs to be done to make this go away, this threat. We're relying on 2 assumptions here to be able to crack this. First, it's using this decade-old cipher with only 64-bit key and the added statistical weaknesses that make it much easier for us to break. That's one assumption. The second assumption is the phone is sending predictable data in a control channel. if there hadn't been the 7th packet, and in fact 4 others had disappeared too, we would have had a much harder time breaking this. And if there's no predictability at all in the data, perhaps we can't break it anymore. Now, these are all the packets that we know of are predictable. They're either going up or downstream. They either send once or periodically. But generally, all this data would not need to be encrypted because it's known anyhow to everybody who cares and doesn't care. We just broke, by the way, a mobile terminated call, and we did look at these LabDM packets. Now, all of them are predictable, of almost all of them. If I go back to the raw data here, oops. Oh, gosh. Let me actually show that in the Wireshark. Almost all of them are predictable, like this one, because of the filling pattern at the end. This packet, where does it actually start? This packet, which we broke, contains as data 030301, and the rest is nothingness. It's 2B, GSM's idle pattern. Now, this pattern does not need to be there. Nobody's using it. This is extra information that could very well be filled with randomness, right? Same with a couple of other packets. This packet is almost all nothingness. This one is too, and so forth. A few packets, like the system information, they are filled a little different. In this case, for instance, with a lot of zeros, but it still seems a lot of redundancy here that could very well be filled with random data, right? So pretty much everything that we can use to leverage our attack is unnecessarily easy to break. Exactly these 2 Bs and the zeros up here, which led to GSM-8, the umbrella organization of the GSM operators, to standardize 2 years ago that these 2 Bs should go away and be replaced with just random junk. Now, do you think this tiny software patch, that's very comparable to the patch Dan Kaminsky called for in DNS 2 years ago, where he just wanted static numbers or counter numbers to be replaced with random numbers. Do you think that has been implemented anywhere? We have not seen it. Tiny patch, replace 2B with a random number generator, software only, and still it's not being seen in the wild. So now that you all understand how to test whether you can crack your own phone calls, please do so and put pressure on your operator to install this software patch. It will defeat not just our cracker, which is a research tool, but in particular also the commercial crackers that are already out there and have been cracking politicians and businessmen's phone calls for many, many years. So please put pressure on the operators for this to happen. It has been standardized. Oops, this is wrong, this number. This is just the filler. On our website, the right GSM specification is linked. Everybody should be doing this. Of course, the phone companies should be doing this too. Say BlackBerry, for instance. This phone